Hello, we're Mark and Jiro, and we're here to discuss the relation between derivatives and continuity. First, let's review ourselves about the definition of a derivative. There are many ways in writing this, but we'll write it as the derivative of our function at point C. This is Lagrange notation with this f prime. The derivative of our function f at c is going to be equal for the limit as x approaches c of x minus f of c over x minus c. At first, when you see this formula, and we've seen it before, it looks a little bit strange, but all of it is calculating the slope. This is our change in the value of our function, and you could think of it as our change in y. If y is equal to f of x, and this is our change in x, and we're just trying to see what is that slope as x gets closer and closer to c, as our change in x gets closer and closer to 0. We're going to make a few claims in this video, and this is more to get on intuition. So our first claim is that we're going to make if f is derivative at x equals c, then f is continuous at x equals to c. What we're saying that if we know it's differentiable, if we can find this limit, if we can find this derivative at x equals c, then our function is also continuous at x equals c. It doesn't necessarily mean the other way around, and actually we'll look at a case where it's not necessarily the case. The other way around, that if you're continuous, then you're definitely differentiable. But another way to interpret what we wrote is, if you are not continuous, then you definitely will not be differentiable. If f is not continuous at x equals c, then f is not differentiable at x is equals to c.
So we'll give a non-continuous function and try them to think about what would be able to find its limit. The first is where you have a discontinuity. Our function is defined at c. So we'll give a non-continuous function and try them to think about what would be able to find its limit. The first is where you have a discontinuity. Our function is defined at c. It's equal to its value. But you can see as x becomes larger than c, it jumps down and shifts right over here. So what would happen if you were trying to find this limit? Well, remember, all this is a slope of a line between when x is the same arbitrary value. Let's say it's out here, so that would be x. This would be the point x comma f of x, and then this is the point c comma f of c right over here. So this is c comma f of c. If you find the left side of the limit right over here, you're essentially saying, yes, let's find this slope. And then let us get closer, and let's get a little bit closer, and then let's find the slope, and then let's get x even closer, find the slope. And in all of those cases, it would be 0. The slope is 0. So one way to think about it, the derivative or this limit, as we approach from the left, it seems to be approaching 0. But what if we were to take the x's to the right? Instead of x being there, what if we were to take x right over here? Well, for this point, x comma f of x, our slope, if we take f of x minus f of c over x minus c, that would be the slope of this line. If we get x to be even closer, let's say right over here, then this would be the slope of this line. If we get even closer, then this expression would be the slope of this line. And so, as we get closer and closer to x being equal to c, we see that our slope is actually approaching negative infinity. And most importantly, it's approaching a very different value from the right. This expression is approaching a very different value from the right as it is from the left. And so, in this case, this limit up here won't exist. So we can clearly say that this is not differentiable. We are going to give you a sample problem. If you want to solve it, you may pause the video. Here are the choices. Here are the answers. Did you get the answers? If so, good job. Again, we're Mark and Gyro, and thanks for watching.